Hey guys, this is Craig Migliaccio from AEC Service Tech, and today what we're going over is reading compound manifold gauge sets and understanding saturated refrigerants so that you can check the refrigerant charge of an air conditioning system. Right now, we're going to be going over a part of a PowerPoint that we have for sale over at our website at aecservicetech.com, and here we're going to be using maybe about half of the slides that are included in the PowerPoint itself, so you can use this to teach technicians within your company, or if you're a school, you can use this within the classroom. So here we go. Over on the left-hand side, you see we have a blue gauge, and that's for the low pressure side of the system, which is also referred to as the suction or the vapor side. And you see that the pressure on the outer ring, which is the PSIG increments, it only goes up to 350 PSIG. Over on the right-hand side, you see that you have a red gauge, and that's for the high pressure side of the system, and that's also referred to as the liquid line. You can see that the pressure actually goes up to 800, so it's a much higher pressure than on our vapor gauge. Also on our vapor gauge, we have a vacuum reading, and that's in inches Hg, so inches of mercury of vacuum. So that is in the green section right here. Manufacturers make compound manifold gauge sets with multiple different types of refrigerant that can be on the gauge face itself, depending on the application. In this case, we have R22, R410A, and R404A. So on the gauges right here, you see we're reading 217 PSIG on each of these gauges. And as we move in through this PowerPoint, we'll have these gauges measuring the pressure on refrigerant bottles and on the system itself. So here we're reading the saturated temperature of R22 at any given pressure. Here we have the saturated temperature of R410A. And so R410A, the color is pink or light rose. And we have that indicated by this black line going across right here. So you take your pressure, you bring that into the inner ring for R410A if you're measuring an R410A system or an R410A bottle. And here you see we have R404A. So you just bring your pressure to the inner ring. Now in this example right here, we're measuring a pressure of 169 PSIG on both gauges. So say the gauges are measuring the pressure on a equalized system. Maybe the system has a piston metering device, the system's been off, and so the pressure on both sides of the system is matching. So once again, in this case, we have 169 PSIG. If the system was R22, then you have a saturated temperature of 89 degrees. So you just bring it in from the 169 PSIG to the green inner ring for R22, and you get 89 degrees as your saturated temperature. If there was R410A in the system, then you have 59 degrees. And so that's shown on both gauges, the blue and the red high side gauge. Also, keep in mind that these little increments are 5 PSIG increments. And so right here, you have 100, and then you have 5 increments to get up to 125. And that's the same right here. You have 5 to get up to 125 PSIG. So it's just that the low side gauge, the increments are spread out, whereas the red gauge are a little bit more squished because it goes up to a higher pressure. Also keep in mind that if you had a digital gauge set, it's going to convert the pressure to saturated temperature for you. So you wouldn't need to do it this way. In this example, you see that we're reading a pressure of 217 PSIG. If we were to bring that into the inner ring and we had R22 in the system, then the saturated temperature would be 107 degrees. But if we had R410A in the system, then you can see that it would be 75 degrees. So you can see it a little more clearer because the increments are more spread out on the low side gauge. Now let's start applying what we know. So we have a low side gauge on the refrigerant bottle, and this refrigerant bottle is an R410A bottle because it's pink or light rose. And in this case, you can see in the inside of the bottle, we have liquid in the bottle and vapor. So this bottle is within a saturated state where liquid and vapor both exist at the same time. The pressure being applied on the gauge by the refrigerant is 217 PSIG, and you can see it a little bit clearer with our magnifying glass right here. You bring it into the inner ring and you read 75 degrees as a saturated temperature of the refrigerant. Now we're also measuring on the outside of the bottle with a temperature meter, and the temperature is measuring 75 degrees. So if this bottle was within a room that was 75 degrees for several hours, the room and the bottle and the refrigerant within the bottle would all be at 75 degrees. So that is how you could check to see if you have pure refrigerant within the bottle and if the refrigerant is in the saturated state within the bottle. Everything should match. In this case, we'll take it a little step further, and you see that this bottle is fairly full. You have vapor and liquid in the bottle, whereas this right here, you have mainly vapor and a small amount of liquid. It's nearly empty. However, the refrigerant in both bottles is still saturated. And if the refrigerant is saturated within the bottle, you're going to be applying the same pressure to the gauge, regardless of how much refrigerant's inside of here. So as long as you have some liquid in the bottle and the bottle's not completely empty with only vapor, then you know that you're going to have the same matching pressure. So in this case, it's 217 psig. Bring it into the R-410A inner ring for the saturated temperature, and we measure 75 degrees. That matches the surrounding air temp of 75 degrees and the temperature that the bottle is at. In this picture, the bottle on the left contains 1 ounce of liquid refrigerant, and the bottle on the right contains no liquid refrigerant. So it's only vapor. The surrounding air temperature is 75 degrees, as indicated on both temperature meters. So the saturated temperature of the bottle on the left matches the surrounding air temperature, which is 75 degrees. However, on the bottle on the right, the pressure converted to saturated temperature measures only 40 degrees as a saturated temperature, even though our temp meter is measuring 75 degrees. This shows that the refrigerant bottle is just about empty and no longer contains saturated refrigerant, but only vapor. So in this example, we have PT charts. And remember that the saturated temperature on the gauge face is just a simplified PT chart that's overlaid onto that gauge face. So to read an actual PT chart, you need either temperature or pressure to start. And over on the left-hand side of the PT chart, you're going to have either pressure or temperature. In this case, we're using temperature on the left-hand side. You see that this temperature starts at 0 and continues down to get to 68 degrees, and then it just restarts over here. So this is just a continuation of the same PT chart. To work with this PT chart, we just need a temperature. So if we have a surrounding air temperature of 78 degrees, then we know that the bottle should be at 229 psig if there's R-410A in that bottle. In the case of R22, if we measured a green R22 bottle and it was 78 degrees surrounding the bottle, then the pressure within the bottle should be 139 degrees if it actually is R22 in that tank. So we can use what we learned already to determine what refrigerant is in a used recovery bottle and if it happens to be contaminated. Reusable recovery bottles are identified by the colors gray and yellow. So yellow is on the neck and then gray is in the body of the tank. You should always make sure to note what refrigerant's inside of a recovery bottle so you don't get confused. And in this case, you see that we have a note with R-410A. If there happens to not be a tag on that refrigerant bottle, the refrigerant in the bottle needs to be identified. This can be done by comparing the temperature surrounding the bottle. So that's right here, 78 degrees. So you can compare that with the saturated temperature of the refrigerant inside the bottle. So right here. So in this case, you see that it matches. So we're reading a saturated temperature of R-410A at 78 degrees, and that matches 78 degrees right here. If we were to do that on a PT chart, we can just come over, and if we measure 229 psig, we bring it over to the temperature column of 78 degrees, and you see that that matches. Even if the bottle has a refrigerant tag, make sure to check the saturated temperature of the refrigerant in the bottle before use. There could be a problem with that tank where you have air that may have got sucked into that tank, maybe from a leak in a system or something like that, and that may have contaminated the bottle. But now you're getting ready to reuse it again. You want to check the pressure and the saturated temperature of that recovery bottle and compare that to the temperature surrounding the bottle, just to make sure that the refrigerant is not contaminated before you use that bottle again. Here's an example of a contaminated refrigerant bottle where we have 259 psig, and that's right here. And the pressure converted to R-410A for the saturated temperature is 86 degrees. So it's a little hard to make that out, but that is 86 degrees as a saturated temperature. However, the temperature surrounding the bottle is 78. So if you have air contaminating the bottle, the pressure will be higher. And so once again, here's another example using the PT chart, 259, and you convert that to the saturated temperature of R-410A, it's 86. However, the bottle temperature is actually 78, even though the bottle has remained at a steady temperature, say in a room for several hours. Now we're going to apply what we know to measuring the pressures on an actual HVACR system. So it's possible to determine the type of refrigerant in an often equalized system. So you see that our pressure on both the high side gauge and the low side gauge matches. And as long as you have a piston orifice, which is the small little fixed orifice usually at the beginning of the evaporator coil. If you have one of those and the system's been off, then these should be equalized. If you have a thermostatic expansion valve, it may not completely be equalized. Just remember that if the high side and the low side gauge match in pressure, the entire system is within the saturated state right now. All the refrigerant is saturated. Liquid and vapor exists throughout the whole system. The pressure right here on the gauge measures 222 psig, and if you convert that to the saturated temperature, you measure 76 degrees, and that matches the surrounding air temperature of 76 degrees and the temperature applied on the actual line itself. And in this case, it's like the perfect scenario, but normally it's not that perfect. But in this case, the inside temperature is also 76 degrees. But this particular scenario works great on a package unit where the refrigerant is entirely outside in that outdoor unit. On a split system, it can be a little harder because you have an indoor temperature that differs from the outdoor temperature. The type of refrigerant can be determined using the rating plate. So it'll say the type of refrigerant on the outdoor rating plate. You can also look if there's a tag on the compressor on the outdoor unit, and you can also look on the head of the TXV if there is one equipped. So as a thermostatic expansion valve, if there's equipped, it should say the refrigerant in the system. In this case, you see that the outdoor unit tag is worn off. That could just be due to the sunlight or something like that, but it's just completely bleached white, and it could just be gone. That's another thing that could happen. In that case, you need to identify the type of refrigerant that you're working with before you just go ahead and slap the gauges on and start trying to measure your refrigerant charge. You can also use a refrigerant analyzer, and that would tell you what refrigerant's in the system. But in this case, we're just going by the gauges and temperature. In this case, we're giving an example of a contaminated refrigerant charge within the system. So the refrigerant is contaminated with air in this scenario, and you see that we're reading a pressure that's very close to 300 psig. It's right around, say, 297 psig. If we were to bring that into the inner ring, you see that it's much higher than the temperature surrounding the unit. So in this case, we're reading a saturated temperature of 95 degrees for R410A, and we're reading a air temperature and line temperature of 76 degrees. So you can tell that the refrigerant in this system is definitely contaminated. And it's usually contaminated with air if it's going to be that high, or nitrogen, something like that. Here's an example of a system that's severely low in refrigerant. And in fact, so much refrigerant has leaked out that there's no more liquid refrigerant in the system. So it's no longer in the saturated state. The system is off. And we see that we read a pressure of 110 psig. We bring that into the saturated temperature of R410A because that's what's stated on the rating plate. And you see a saturated temperature of 36 degrees. That is way, way lower than 76 degrees. And that's what we should have, 76 degrees. You see we're measuring the temp here and outside. And so that is a indication that this entire system is severely low due to a refrigerant leak without even having to turn the system on. We've skipped ahead in the PowerPoint, and now we're checking the charge on a running system. However, before you do that, you want to make sure that you have good indoor airflow matched to the system size on the outdoor unit rating plate. You also want to make sure that you know what metering device is in the system, so you know how to check the charge. You also want to know what refrigerant's in the system, and you want to also allow the system to run for, say, 10, 15 minutes before checking the actual charge. However, you do monitor the gauges, so I go over all that stuff in the PowerPoint. But in this case, you see that we have a thermostatic expansion valve as the metering device at the indoor unit. We're going to be using the subcoiling method. So now we're applying what we know, and so you know how to read the gauge sets, and you know how to convert that to saturated temperature. So the red high side gauge is actually measuring the saturated temperature of the refrigerant in the outdoor unit while the system is running. The blue gauge is measuring the saturated temperature of the refrigerant in the indoor coil while the system's running. But in this case, we're going to be using the subcoiling method because we have our thermostatic expansion valve. We need to check the pressure on the high side gauge. We're going to convert that to saturated temperature. And we also need to take a measurement on the small liquid line. And you see that we're measuring 92 degrees right there. So our saturated temperature for R410A refrigerant on this particular unit while it's running is 104 degrees minus the liquid line temperature is 92 degrees, and we're left with a subcoiling of 12 degrees. So this is how we check the charge of a system with the thermostatic expansion valve, is with the subcoiling method. The target subcooling can be found on the outdoor unit rating plate. So in this case, it says a TXV subcooling of 12 degrees. In some cases, it may have multiple different TXV subcoolings depending on the outdoor temperature. You may also find the target subcooling on the inside of this shroud right here. It may not be on the rating plate, it might be on the inside of the shroud. If there's no target subcooling posted for the unit in air conditioning mode, a target subcooling of 11 degrees can be used on single speed or 2-speed units. So now we need to compare the actual subcooling to the target subcooling. So you find your subcooling from the saturated temperature on the red high side gauge minus the actual liquid line temperature. So that's the small liquid line. If the actual subcooling is less than the target subcooling, then you need to add refrigerant to the system. If the actual subcooling is higher than the target subcooling, then you need to recover refrigerant. And the correct refrigerant level is if you have the actual subcooling is within plus or minus 3 degrees of the target subcooling. So preferably it's right on the target subcooling or just slightly higher, maybe 1 degree higher than the target subcooling. So that would indicate a correct refrigerant charge level. In the PowerPoint, we have detailed examples of a system that's low in refrigerant, a system that's overcharged, and one that's a correct charge. But now let's go move on to the total superheat method. So if we have a system that has a fixed orifice, and a fixed orifice could be a piston or a capillary tube metering device, then we're going to use the superheat method. And since we're measuring it at the outdoor unit, it's going to be considered the total superheat method. So in this case, we have our pressure converted to saturated temperature, and we have a saturated temperature of 42 degrees. We're also going to take our actual line temperature on the vapor line, and you see that we're measuring a temperature of 56 degrees. In this case, it's reverse from subcooling. So you got to remember that it's the actual line temperature minus the saturated temperature. When we were working in subcooling, it was the saturated temperature minus the actual temperature. So you just got to remember that they are reversed from each other. So we take 56 degrees as our actual vapor line temperature minus the saturated temperature on the blue low side gauge, which is 42 degrees, and we come up with 14 degrees of total superheat. Now we need to compare the total superheat to the target superheat. Target superheat is found by first measuring the indoor wet bulb temperature, so at the indoor unit, and also the dry bulb temperature surrounding the outdoor unit. So it's actually the air that's getting sucked into the outdoor unit and getting blown out the top. So you got to take it down low. So you don't want it to get affected by the heat that's being rejected above the unit. So in this case, we're reading an 85 degree dry bulb standard air temperature entering into the outdoor unit. You can input the WB and the DB temperature into a superheat chart, or you can enter into an app, a digital calculator, or a calculation tool like we have over at our website at acservicetech.com. In order to measure the indoor wet bulb temperature, you're going to have to measure it within just a few feet of the evaporator coil. So in the return duct, if you have a grill that's really far away from where the unit is, the temperature can change. The wet bulb temperature can change by the time it gets to here. Maybe that return duct is running through an attic or something like that. So you really want to get it as close to the air handler as possible. To measure the DB temp, you want to make sure to measure about a foot away from the outdoor coil in the shade, away from the hot discharge air exiting the coil. And this can be done with a standard temperature reader. Make sure to measure the indoor wet bulb temperature with a digital psychrometer. You could also do it with a sling psychrometer or also a standard temp reader with a wet sock over the bead temp sensor. But we have other videos on that linked down in the description section below, so you can go ahead and check them out. In this example, you have a DB temp, so that's a dry bulb outdoor ambient temp. So it's either OA, it could be referred to, or DB, that's the outdoor ambient temperature, 85 degrees. Our indoor wet bulb temperature is 68 degrees. We input them onto a target superheat chart, and we have our indoor wet bulb temperature is 68 degrees, so you bring that down, and then you have your outdoor DB temp, and you bring that across, and you come up with 19 degrees as your target superheat. Depending on what you use to calculate your target superheat, it may be, say, 1 degree off from each other. You know, you could use a digital manifold gauge set, and that'll come up with the target superheat automatically for you. You could use a calculator, an app, a calculation, charts. But we have a full article on all that stuff over at the website, so you can read that over at acservicetech.com. In this case, we have a target superheat of 19 degrees. and that's presently. You got to remember that as the system runs, your indoor wet bulb temperature is going to lower because it's taking the humidity out of the building. So your target superheat is going to change while the system's running. So you constantly have to monitor your indoor wet bulb temperature while you're checking the refrigerant charge and while that system is running. Now we need to compare our total superheat to the target superheat. And you see that we have the actual line temperature on the vapor line minus the saturated temperature found on the blue low side gauge. And that's how we come up with our total superheat. If the unit was low in refrigerant and we needed to add some refrigerant, obviously you're going to find your leak first and see if you can fix that leak. But if you need to add refrigerant, your total superheat is going to be higher than your target superheat. If you are overcharged and you need to recover some refrigerant, your total superheat is going to be less than your target superheat. And if you have the correct refrigerant level, your total superheat is going to be within plus or minus 2 degrees of your target superheat. And once again, we have detailed examples in our PowerPoint discussing each one of these. So we have our undercharged, our overcharged, and our correct charge. If you want to learn more about preparing a system for refrigerant, checking the refrigerant charge, and also troubleshooting, check out our book, The Refrigerant Charging and Service Procedures for Air Conditioning. So we also have a 1,000-question workbook that helps you to retain your knowledge that you're learning from the book. Now, this workbook also has an answer key so you can check your answers, so it's a self-study guide. And we also have our quick reference cards that can be used out in the field right next to the unit while you're checking the charge or troubleshooting. We have all these resources available at our website at acservicetech.com/acbook. We also have all of our physical products available over Amazon and also eBay. And we have our ebook over at the Apple Bookstore and also on Google Play. Hope you enjoyed yourself, and we'll see you next time at AEC Service Tech channel.